Good?
Yep.
Hello. Where would you like the setup?
If
This angle over there?
probably this angle to complement the camera, so it goes from the right side to another one. You may sit here and place camera so that you control what is going on.
All right.
But I trust your sense of, how to say, artistic sense.
Artistic sense. I don't think anybody's ever accused me of having artistic sense before.
Is this magnification big enough, or it should be a little bigger?
That's great.
I mean, yeah, when it catches both speaker and the content.
I can read it from here.
You can?
Yeah.
Whoa.
I'm just seeing, I don't think.
Then we need to
the battery will die.
redesign it because people will walk to the stage from this side.
I don't think I think it'll probably be fine, but just as
Do
a
you need to
backup.
recharge it? Oh, okay.
Yeah.
One can put it from this angle, but then the screen will not be visible.
Thank you.
Was it blocked from
Yep.
what's it? had a laziness attack to myself last night. I was planning to help and instruct on putting orbitals on the top and the bottom,
Oh yeah.
but then I decided, no.
Yeah, I thought about it too. I didn't want to.
It would take maybe 3 minutes more, but I was on the like, okay, no. Enough for today.
I was gonna say I had the same problem because I kept changing things, and I figured this would just be a slippery slope. So I
Do
gotta
we
stop
need to
sometime.
pasture?
Yes, because we don't have key.
It's unlocked.
You may check. Wait, double check, please.
Yeah, it's
It's
unlocked.
unlocked.
Then trash can be removed.
You probably each take like 5.
I do 3. So you were exacerbating.
You came prepared.
Yeah.
You decided not to edit the
No.
slides, but make demonstration.
So yesterday, or on Tuesday night, I was up until like 2 a.m. watching the election. So then I was like, I need to get to bed. So I sent it to you, and I immediately went to sleep. So then I saw it, and I was like, oh no, whoopsies. So I just made it.
Good. And I decided, okay, for a person who did good talk on the second year, the requirements should be above, and critique should be hard.
I printed the important page. So if anyone asks about oscillator strength,
You show this tiny script and look here.
I can write it on the board.
Oh, then we need to turn camera if you want it. Okay, well, do whatever is needed.
But are we using that camera?
No, we are using this camera.
So then,
If you check direction of a camera several times,
oh, then this
It-
has
it's
to
right.
move.
it is okay, but there is a chance of failure. We did it when we met first time,
Oh,
and then the recording was inactive.
I guess I could always just walk up to the screen and be like, "This is it."
Yeah. Yeah, you good.
I guess I just figured that light to matter interaction would include the overlap.
Oh, that's way cool.
Okay. How to get oscillator strength.
Well. Same thing.
Yeah. So
For us, he'll probably show this tree definition, which applies. Hmm? What do you mean?
for Oswald?
No.
I thought you said for Oswald.
No.
Oh.
Symmetry.
Yeah, I heard that part, but I heard
Applies.
for Oswald.
That's assuming he gets it up to that.
Oh, he's not until 1:10.
I definitely have problems with putting together schedule. Last times the numbers were off, it was like going backwards in time. Now I labeled 12 a.m.
Midnight.
Yeah.
Oh.
And then I asked Amy to advertise it to the department.
I saw it.
I just looked at the numbers this time.
This is why the 24-hour clock is so much nicer.
Or just don't put it. And if someone's here at midnight,
How many jobs active? I think Whitney has enough time to represent. You have enough time.
I did a little
they're all.
mistake in the schedule, and it shows AM instead of PM. And from your talk to the next talk, there is a gap of 12 hours. So you can speak long enough.
sad. The water, you can't do coordination.
Well, that's because by default, they consider it a saturated molecule, right? And those are programmed covalent bonds anyways.
I know. But when I make
Okay. It will be great if we will get some guests, but even if, well, we already have one guest. Yes. It is lecture number 23 in the computational chemistry course. We do have, as usual, the biggest possible challenge is to match time schedule. You all accumulated so much knowledge and information, and you are so eager to share it that it is very difficult to fit into 3, 4, maximum 5 minutes presentation. So please watch time. If you will go longer than assigned, I will just come up and stop. So try to speed up. The idea is that we do have 1 minute to come, 1 minute to leave, 3 minutes presentation, 3 minutes questions. But it can be modified a little bit for the 4 minutes presentation, 2 minutes questions. For the visitors, who are very welcome, for the visitors, you are very welcome to ask questions and support scientific discussion, but please make note that we are on a tough schedule. Each talk is like 3-4 minutes and questions no more than 2 minutes. If you fail the schedule, we will be kicked out and the last speakers will have no chance to present. So we are living a tough life. This is a computational chemistry course. The goal is to provide students in engineering, math, chemistry, physics with practical skills to model, to characterize materials. The course is composed of 3 main components: theoretical background, practical skills, and scientific communication. As you see, today we will practice scientific communications, presenting our practical skills. Before we learned different pieces of software, but now we are focusing on a specific piece of software named Vienna Ab Initio Simulation Package, which is designed to model not only chemical systems, but chemical systems interfacing solid surfaces, liquids, gases. And upon completion of this set of presentations and accumulating these skills, we are going to try to apply those to modeling realistic materials and predict several observables, such as chemical stability, magnetization, band gap energy, absorption, photoluminescence, spectra, and reaction barrier for bond breaking and formation. So with this session, with this piece of software, we are trying to go further than we did with other pieces of software, because we are having at least 3 new challenges that will be addressed by each of presenters from different angles. So first, periodicity. If we depart from isolated chemical molecule to periodic models, there are specifics for periodicity. Second, spin multiplicity. If you depart from singlet closed shell molecules, one needs to make special arrangements for spin. And third, if there are chemical reactions that we are interested in, we need to have tools to track bond breaking and formation. With this, I would like to bring your attention to the schedule, which consists of 10 talks. We will try to follow the schedule, and today meeting completes 4th chapter in the course. There will be 3rd chapter. There will be 4th chapter also finished with presentations. And I would like to bring your attention to the fact that your presentations are placed here. They are numbered according to the order, 1st, 2nd, 3rd, and they have name of the presenter in the name. So 1st, 2nd, 3rd, so you will be able to navigate. So I'm opening the first one, bringing it, and you will be seeing the title page, but then you will see your own title page. Okay? So with this, I would like to invite H.M. Faisal Nasrallah to give a opening talk on the input that one needs to communicate to the VASP software to make it running. For yours, please be short. So here's keyboard, mouse, screen, point on the.
Thank you. Hi everyone, good afternoon. This is H.M. Nasrullah Faisal. Today I'm going to talk about the goals and responsibilities of DFT and preparation of input files for VASP. Actually, density functional theory, abbreviated as DFT, uses the electron density to find the energy of a molecule instead of wave function. Actually, it is one of the newest ab initio methods and it has become popular due to less intensive calculation. It was originated from the theorem by Hohenberg and Kohn, but the original theorem was used for the ground state electronic energy of a molecule. The practical application of DFT was developed by the Kohn and Sham. In DFT, the electron density is actually expressed as a linear combination of basis function known as Kohn-Sham orbitals. A determinant is formed from these orbitals which is used to compute the electron density. The Kohn-Sham orbitals are not mathematically equivalent to Hartree-Fock ones. A whole list of density functionals are used as the exact density functional is unknown, and these functionals are developed either from quantum mechanics or by parameterizing function. In density functional theory, the integrals for Coulomb reduction is needed to be done over the electron density, which is scaled as n cube. In case of Hartree-Fock, this is scaled as n4. That's why the density functional calculation is quicker than the Hartree-Fock calculation. Density functions can be broken into several classes, and the simplest one is the local density approximation. For high-spin systems, it is known as the local spin density approximation, and it is widely used for the band structures. The accuracy of the DFT can be poor to fairly good depending upon your choice of density functional and your choice of basis sets. For organic molecules, the B3LYP hybrid potential with 631G basis set is most popular because of its effectiveness, but the accuracy and effectiveness of DFT is not very good for the heavy elements, the charge system, and the systems that are sensitive to electron correlation. Now the VASP. The Vienna ab initio simulation package is a computer program computer program for atomic scale materials modeling like electronic structure calculation. It computes an approximate solution by using DFT or Hartree-Fock or by combination of both. In VASP, the one electron orbital, the charge density, and the local potential are expressed in plane wave basis sets. The interaction between the electrons and ions are represented either by pseudo potential or by the projector augmented wave method. Now the most important input files for VASP are POSCAR, POTCAR, INCAR, and KPOINTS file. The POSCAR file, it contains the lattice geometry and ionic positions. Sometimes it also contains the starting velocities for an MD run. The POTCAR file, it contains the pseudo potential for each atomic species that comprise the molecule. For the KPOINTS file, this contains the coordinates and weights or the mesh size for creating the K-point grid. And the INCAR file, actually it is the central input file for the VASP. It determines what to do and how to do it. So that's our structure. There's the cyclohexane structure. We made it in Gaussian and then optimized by Hartree-Fock. Now if we need to make the POSCAR input file, we need to convert this Gaussian structure into XYZ file, and that's why we convert this Gaussian Hartree-Fock file into the XYZ file, and then we convert this XYZ file into POSCAR file. If we need to edit this POSCAR file, we type the nano POSCAR and then we will get this file, and we will remove the unexpected lines from it and we will make a clear one like that. Now we need to rotate the XYZ as we need to align it according to a required orientation with respect to XYZ axis, and then we need to put the angle of rotation around X, Y, and Z. As a result, an intermediate postcard.tink xyz will be created. Now we need to define the periodic lattice vectors, and we need to put the lattice correction on the x, y, and z axis, and then we submitted our postcard file. Then we need to make the INCAR file. There's the INCAR geometry optimization, and if we type the nano INCAR, we will get those different modules that control this operation. In this case, as it is a single point charge calculation, we change the NSW from 150 to 0 like that, and then save it. Now the KPOINTS file, for the KPOINTS file, we will write this code CP being KPOINTS, and it's done. And the last one is the postcard file. It is the potentials of each atom, and we need to write this code, and in this case these are the atoms that comprise the molecule, and that will be ordered according to the alphabetical order. Now we do have all the files. If we put it in we can look the postcard, KPOINTS, INCAR, and postcard, and now we can run our VSP, and that's it.
Okay, let's thank Faisal. So, any questions to whatever he presented? Please.
So do you use serial version or parallel version of VASP? So if you use parallel version, how many processors is the optimal number for your calculation?
The larger the better. Just totally.
How many processors you usually use? 8, 16, 100? No?
I'm not at the camera.
It's actually 4. 4.
4? Only 4? Yeah. And I use
Small system.
This
it's a very small system. Yes.
More questions?
So you said that heavy elements were not DFT friendly. How heavy? Are we talking uranium, iron, potassium? How big? How far down the periodic table is DFT still useful?
I think the heavier ones, like that you talked uranium or titanium, that heavy ones maybe.
Okay, more questions? You gave practical steps how to prepare input file for positions. If you do not use periodic models, if you use chemical models, what are the good values for this periodicity adjustments? Approximately.
Here?
Mm-hmm.
0, 0, 0.
Just what are you showing here? How much vacuum do you add to simulation cell? In which units are those numbers?
There's are the lattice corrections.
Yes, in which units?
Angstroms.
Good, thank you very much. Nice presentation answering questions. And with this, let me invite next speaker to the stage, which will be Tion, Nakasinha, and Mindika. So, next speakers, please try to approach and set up your presentation while we are going through a session. And just one more announcement. One of the side goals of this session is that one person becomes expert in one aspect, another in another aspect, and then we communicate, so to say, verbal manual how to operate this software. So it is not just to show how nice I know about it, but it is a little teaching assignment, communicating skills. Okay, with this, Timon Mindika Nakasinha, PhD candidate in the surface chemistry, will present which output VASP software is providing. Floor is yours.
Okay, good afternoon everyone. So during my presentation, I'm going to show you how to extract some important information contained in VASP output files, and also how to visualize so-called Cornsham orbitals. So as Faisal discussed earlier, we can run a VASP job using this set of input files, this POSCAR, PODCAR, INCAR and KPOINTS file. And if we run a VASP job using this set of input files, a set of output files will be generated like this. So if we generate this set of input files, this will contain unique pieces of important information. So for example, this CONTCAR file contains updated geometry data such as lattice points, Bravais matrices, ionic positions, etc. And these WaveCar files contain the important wave function informations, wave function coefficients. OCCAR file contain short summary of the results. So we can use this CONTCAR, ChargeCAR and WaveCar files in continuation jobs such as molecular dynamics calculations. So in my part, I'm going to so using outcar file, we can extract some important essential information for a particular system, such as total energy, band energies, home volume energies, etc. So using an example, output file for titanium hydroxide, which was optimized, with a single point optimization. I'm going to explain how to extract total energy and band energies for this particular system. So if you want to extract total energy of this system, if you have the outcar file, we can use this command line with the command grep and this keyword free energy. We can extract the total energy with this command line. So it will give the total energy in electron volts. So if you want to extract number of bands of this system, which will be a important input in lot of calculations or a lot of calculations, we can find out the number of bands in the system using this command line, grep, and the nbands keyword with this outcar file. We can generate the number of bands in the system, and if we can generate the band energies, we can find the band energies of this particular system using this command line grep, and this is the number of bands in this particular system and the keyword band energies and our outcar file. So this will be the output. So if we know the band energies, we can find out the highest occupied molecular orbital and the lowest unoccupied molecular orbital. So here you can see the band number, band energies and the occupation. So if we know the energy of the highest occupied then lowest unoccupied molecular orbital, we can find out the band gap in electron volts. So these are some essential information which we need to know about a molecule. So now I am going to explain briefly about how to visualize Cornsham orbitals using this VASP output data. So Cornsham orbitals is an analog of molecular orbitals in Gaussian. So in density functional theory, Cornsham orbitals are defined as some set of auxiliary quantities which can be used to calculate total charge densities and the total energy. So this relationship shows how to use. So here we can see the relationship between the total density and the Cornsham orbitals. So if we know the Cornsham orbitals, we can determine the density, and if we know the total density, we can determine the total energy, because total energy is, we can represent the total energy as a functional of the density. So to visualize Cornsham orbitals, first we have to generate these Cornsham orbitals. So to generate these Cornsham orbitals, we can use set of input files. We can use the output files of the optimization job. So here the positions, we can use the positions of this output CONTCAR file as the POSCAR file of this input as the input file, and then we can use the same K point and the potentials for this calculation, and also we can use the WaveCar file from this output file of the optimization job, and we have to import we can import the necessary INCAR template which is necessary to run this particular calculation job. So we have to import this. We can import this INCAR template, and we can modify this template according to our system. So in this case, I am doing optimization of the titanium hydroxide molecule. So, which has so this is the INCAR template. I have to modify this according to the according to this molecule. Here I have 24 bands in this molecule, so I have to modify this, and I have to modify this part in energy interval, which is characteristic to the band energies of this molecule. So after modifying this INCAR file, we have all the necessary input files so that we can run this calculation. So it will generate this output data. So here you can see these partial charge densities, which are the cone-charm orbitals for each and every orbital in this molecule. So if we since we have these partial charge densities for the cone-charm orbitals, we can visualize these orbitals using any kind of software like VASPview or vaspview. So here I am going to show you how to visualize this using vaspview. So I'm going to visualize the molecular orbital, highest occupied molecular orbital of this titanium hydroxide molecule using vaspview. So this is the vaspview data viewer window. So we can open this molecular orbital, highest occupied molecular orbital of this titanium hydroxide using this vaspview software, and then we can customize this window using these tabs: data, atoms, bounds, view and options tab, to obtain a nice image of this molecular orbital. So that's all I have. Thank you.
Okay, let's thank for nice presentation. And floor is open for paper is open for discussion. Any questions to Tilan?
Still a good comment. I mean, instead of using vaspview, you can use Vesta. I think Vesta is also quite good to visualize.
Vesta?
VESTA.
Okay.
It's free software. It's very similar to Crystal Maker or something, and it's free.
Okay.
And it's for visualization. It looks really good. Okay.
Can you directly visualize using the vaspview?
Yeah, you can visualize charge densities.
Okay.
And
so if you want to do like
in general,
if you want to use Gauss view, we have to generate the cube files. So we can directly do, but
for Vesta you can open the Jacka file or Barca file directly.
Okay.
You don't have to do any conversion, because in the past I remember I had to do conversion. With Vesta it's quite convenient.
Okay.
Thank you for the comment. More questions to the speaker? Which orbitals do we see here? S, P, or D? On which atom are they localized?
P orbitals of oxygen.
Yes, very good. Let's thank Tilan once again. So the next presentation is by Aaron Forley, and he will help us to address one of the he will help us to address one of the key challenges for periodic systems: the ability of all system of electrons to travel with a specific momentum. Floor is yours. We are about 5 minutes behind the schedule, but so just try to be quick.
So I'll be explaining the purpose of the KPOINTS files that we use in VASP. So before going into VASP, I'm going to explain what a K-point is, physically. So comparing small molecules and periodic structures, if we have an acetylene molecule, we can model it as a particle in a box. So if it tries to move, the electron will just kind of bounce back and forth, and here it'll produce a standing wave and have a zero average or zero group velocity. But if you're in a periodic potential well, like a polyacetylene molecule, the electron can tunnel through these potential barriers here, so it can have a velocity in one direction. So if the electron has velocity, it can have some momentum. And then using the de Broglie relation, we know that momentum is h over lambda. Making use of a convenient change of variables to make it a linear equation, we can change that into the momentum is h bar k, where k is 2 pi over lambda, or the wavelength of the electron. So that is the k that is referring to for k points. So we're essentially plotting electron momentum with our k-points file. So as you can see in the fourth row, the 1, 1, 1, that corresponds to plotting one k-point and the 3 k-point directions x, y, and z for your periodic directions. So if you change those, like we change the first column into 4, that'll plot 4 k-points along the x direction and 1 along the y and z. So you just have to know which direction your model is periodic in to change the number of K points that are sampled in that direction. And so if the electron has changing momentum, it'll have changing energy as well for each orbital, which will lead to electron or energy dispersion in the periodic crystal. And thankfully, that it's periodic throughout the crystal as well, the dispersion relation. So we just have to sample the smallest repeating unit, which is the Brion zone. And that's where the K point sample. And then the Brion zone corresponds to the lattice vector, or the length. And then the wave function solution is the general solution of the Bloch function, and that's what is plotted into to get the energy. So if we have our wave function, we can get our energies. And on the right, that shows just the dispersion relationship for trans-polyacetylene. So how do we practically generate the energy dispersion files? So for here, I just plotted the HOMO and the LUMO. And we say we run VASP with the desired amount of K points, and we inspect our INCAR. We'll have a bunch of K points, like clusters. So for K point 1, we'll have a K value and a bunch of energies. And different K point will have different energies for the same orbitals. So here I'm applying the HOMO LUMO, so 10, 11 orbitals from the output. So first we want to extract the K points. So the top line just explains how to pull out the K point files and save them as a KK file, which shows the 4 K points that I plotted. And then we want to extract the orbital energies. So grab the 10th orbital energy, save it as K10, and it saves the 4 corresponding orbital energies for those K points. And then do the same thing for the 11th to get the LUMO orbital energies. And then we want to merge all those into one file so we can plot them using NuPlot. And then we have to have them in columns because that's how NuPlot reads it. So using this top file, that merges them all into an energy dispersion file where we have our K points, HOMO, and LUMO energies. And then we can just write up a little script for NuPoint to plot each of those. And then get the nice little graph that I have on the right showing the energy dispersions for the HOMO and the LUMO. So in summary, for molecules, you only have to plot 1 K point since it doesn't have any changing momentum. For periodic structures, you have to plot multiple K points along your periodic directions. And then K points give instructions how to plot the K points so we can plot our band structures for the materials.
We thank Aaron for and questions are very welcome to be thrown at him.
The student had to ask a question, right?
Yes, and I'm recording. Well, it is on record who is asking and who is not asking questions.
Okay.
Me again. So how do you choose which direction that you vary the K point values?
You mean in the VASP?
No, I mean you have to choose different K point along a certain direction, right?
Mm-hmm.
How you choose that direction? How do you know which direction that you should get?
Oh, so if we go, so if we look here, like this will correspond to the x-axis.
Okay.
This column, the second column is the y, and the second column or the third column is the z.
Yeah, but which direction that you should go, right? It depends on the molecule that you're looking at, right? It depends.
Oh, you just have to know from when you make it, I guess.
So for example, you can choose from the gamma point to X point, or the gamma point to the Z point,
Oh, you
gamma
mean
point
the-
to the L point in the Boolean zone, right? So which direction that you have to choose?
Oh, so that would be the bottom row. So 0, 0, 0, that's the gamma
Yeah.
symmetric. And then I'm not too familiar with reciprocal space, so how to switch them around, but you do that with the last row.
Let me reformulate the question by Dr. Kong. Are you dealing with 2- and 3-dimensional periodicity, or you are focusing on 1-dimensional periodic systems only?
For this one
So
is
that's easy.
1D.
Okay. Yeah.
More questions? I do have one.
Okay.
So, can you go to your computed dispersion? Yes. So the systems where minimal energy between HOMO and LUMO appears at the 0 momentum are named direct gap semiconductors. The systems where the minimal energy at non-zero momentum are called indirect gap semiconductors. Do you have here illustration of direct or indirect gap?
From there, it looks like a direct gap.
Yeah, very good. Let's thank Aaron. And the next presentation will be by Whitney Ong, and she will continue the aspects of characterizing materials with the VASP software, and she will address the practical way to estimate the gaps. to illustrate what are the gaps, how to compute, and how to process output of VASP. Floor is yours. We are almost in time thanks to Aaron.
Okay, so I'm Whitney, and today I will show you how to plot density of states and molecular orbitals using VASP. So brief introduction, density of states represents the number of states per interval energy that can be occupied at each energy level. So if you have a high density of states, means you have many states available for occupation, and if you have a zero density of states, means you don't have any states that can be occupied by electrons. So the molecule I use to optimize all my structures is C4H4 because this is the smallest molecule that I can run with single K point. So after optimizing your structure, you should run a single step job by modifying your INCAR file. So first of all, you make a new directory to put everything in there, and then you copy, this is the most important one, you copy your concar file and you name it to postcar in your INCAR, to your new file, and then you copy your KPOINTS, podcar and INCAR file, and then you make changes to your INCAR file. So first of all, you have to make sure your to make it into a single step job, you change the NSW equals to 0, and then if you have different electronic configuration like cationic or anionic state, you have to state the number of electrons in your system. And if your system is in excited states, you have to change your I smear to -2 and add the line fairway for a number of occupied molecular orbitals multiplied by 1, and then you type 0, 1, and then number of unoccupied molecular orbitals by 0. So here's the example of the INCAR file. Your NSW should be 0, and this is added according to your electronic configuration. So after the job is done, the density of states can be plotted, but a few informations are needed. So you need a number of states, you need a number of electrons, number of atoms, and the Fermi energy and alpha and beta energy. So first of all, you also have to generate a states file. You can get the band energies from the states outcar and put it into a states file. And in the states file, it's important to delete the first row because we only want the values and not the wordings. Otherwise, it wouldn't work. So, and then it's important to look at the number of band, a number of orbitals, and then you look at which interval you want. So, for example, I want a -9 to 1 electron volt, just a few above the HOMO and few below the LUMO to plot your graph. And then you can get the number of electrons from your outcar file. You can also obtain your Fermi and alpha and beta energy from your outcar file. And then you run the script to generate the density of states, and then you answer the questions according to what they want. And then you can set up your parameters of your graph as well. So this will, you can find your energy and Fermi and alpha and beta. And then if your job is succeeded, you should get this tree line of I am still okay. If it's not okay, well, usually you have one line and then you have error down there. Then whatever new files that is generated will not have any information to make your file. So make sure you have these 3 lines, and then you can move on to the next step. Usually the error comes from when I forgot to delete the first row from the states file. So then you can plot your graph and convert to PDF, and then copy to a local computer and view your file. So the results can be very different from ground states, anion, cation, and excited states. The red color shows that the electron, the orbitals being occupied by the electrons. So you can see that in anionic state we have extra electrons, so there's more electrons occupying the orbitals, and then in cationic state we have less electron occupying it. In the excited states we can see the flipping, or the excited states of the electron occupying the next state instead of the ground state. So if you want to visualize your molecular orbitals instead of from the graph, So you also have to have your optimized structure, and then you should make a new directory because it will have quite a lot of orbital files being generated. So make a new file, and then copies the following files, KPOINTS, PodCar, and one more extra file that you have to copy is the WaveCar. And then again, copy the concar instead of postcar because we want it from the final data, not the initial data. Otherwise, you would not get anything as well. And then INCAR file can be copied from the template in the cluster. And then you also have to modify some changes in your INCAR file. So things to consider is your number of orbitals in the n bands and the range of orbitals you want. So earlier I wanted a few above the HOMO, a few below the LUMO. And and then I just put like -9 to 1 electron volt. And then same thing to go with your number of electrons and your way if it's in cationic, anionic, or excited state. So this is a typical INCAR file. So your number of bands and then your E and IP should remember to change that. And then your last line is always can add all the changes. And then you will see many new files can be generated. You can just make both one HOMO and LUMO, but usually you want a few, then you can visualize it in the VASP. You can copy all these files to the local computer and view it using the VASP file. So go through briefly using how to use the VASP view. So in your data tab, you can adjust your isosurface and see if you want to draw the slice. In the atoms tab, you can adjust the atoms radius. In the bounds tab, you can extend or shrink the bounds. In the view tab, you can zoom, rotate, or move the molecules around, and miscellaneous options can be found in the option tab, like changing the atom's color, background, things like that. So this is the results of seeing. You can view different orbitals from the HOMO and LUMO state. You can view it in the VASP view. So in conclusion, 4 basic files is needed to run the job, postcard, INCAR, PodCar, and KPOINTS in DOS plots. You need to run a single job stat, and you also have to adjust it based on your electronic configuration. And in molecular orbitals visualization, the most important thing is you need an additional WaveCar file in there, and you must remember to copy concar file instead of postcar. Questions?
Let's complete it. Presentation is open for discussion. Levi is
on slide 6. You say you can just hit 6 enter.
Oh.
You say number of HOMO times 1, 0, 1, number of LUMO.
What?
Are you adding 2 additional states to your band? Number of bands?
Oh, sorry, -1.
Okay.
The total should come to the number of molecular orbitals.
good eye. Dr. Kung?
Can you get back to where you saw the anion, cation, and excited state? The density state, yes. So when we look at this, how do we know it's anion or cation or excited state? You have some simple, tips on how to look at this density of state. So how do we know that it's ground state? How do we know that anion? Or how do we know it's cation?
Let me reformulate the question of Dr. Kang. If we close this information and we do not know what are the labels, can one recognize, and we know only that there is the same molecule in different configurations, ground, anion, cation, and lowest excited. Can you point out and explain which of them is, what is the typical signatures of anion, cation, and excited state?
So this one will definitely be excited states because of the different
swapping of the
flipping of
population.
For anion, the electron occupation will be like towards the right, and the cation will be towards the left. If you look at the energy, this is like in -16, and this is like in -2. The ground state will be like in the middle, like -4, -3.
So the signature is the occupation, right? So see whether which state is occupied or empty, right? So for example, in the excited state, you had the empty state below an occupied state. So that means you remove one electron below. So
Very good. More questions? If no, let's thank Whitney once again. And the next presenter is Zachary Gerrits. I'm learning how to pronounce his name for the last couple of years. And the present... Huh?
No worries, no worries.
So his presentation has a key importance because he opens a door. He opens a door into the world of spin polarized models, in the world of magnetic materials.
Rest of the world. All right, so I'm Zach, and I will be talking about how to look at open shell systems in VASP, specifically their density of states. Okay, so what's an open shell system? Well, we all know what valence shells are, and if they are filled, they'll have spin pairing, right? Well, if we do not have spin pairing, we only have one electron occupancy per orbital. In the case of oxygen, we now have an open shell system. So, transition metals also are open shells. For instance, I'm using the aqua metal transition metal complexes, or I should say hexa-aqua transition metal complexes. And the cool thing is, I mean, here's a schematic of the octahedral geometry of a hexa-aqua transition metal complex, but they also have different colors that correspond to their transition energies, and these are DFT transitions. Phew. I'm going to be using specifically the titanium 3+ as a model for generating these density of states. So the biggest difference here, other than acquiring your 4 fundamental files, is what you do in your INCAR file. And so there you can actually adjust what the spin state is. And just to remind you, the spin state is 2 times what the summation of all the half-integer spins are plus 1. And those half-integer spins, remember, that's the number of single electrons, basically, so it's not spin paired. So for instance, for oxygen, it's 2, right? Because you have 2 times 1/2, 1 times 2, 2 plus 1, 3. It's a triplet. Aha. Fantastic. In our case, we are doing titanium 3+. We only have 1 unpaired electron, so it's going to be a doublet. You can change the oxidation state, because otherwise it would just treat it as a neutral metal complex, and then this would be wrong. So that's the number of electrons, and specifically the number of valence electrons. So you don't have to count core electrons here. And so that totals up to 49. Okay, so go ahead, you have your files now, you run VASP, you get a whole bunch of joy. And then if we look into the INCAR file, you will see now that your energies for the generated molecular orbitals are now split into 2 different spins. You have spin component 1 and spin component 2. And so, up, down, basically. And what you should notice is that the occupancy of the HOMOs and the LUMOs are different. So for the spin up, we have occupancy up to 25 orbitals. Spin down, we have occupancy only up to 24. This makes sense because we have a unpaired electron. Okay, so now what we want to do is actually go ahead and generate our density of states. So we need to pull that spin component energies out of our INCAR, place them in these states up and states down files. You want to remove, all the text so that we actually can read the file properly. And then you generate your density of states by using the script, the Dristas up or down. Follow the prompts, so number of states, your energy range of your orbitals, Fermi, alpha, beta, magnitudes, all that fun stuff. If it all checks out, it should be okay. And then, for completion, you want to plot it, right? So plot it with NuPlot, do the file transfer to PDF, and then download it. So this is the density of states plot for titanium 3+, covering basically the whole range. What you'll notice is that it's pretty symmetric where they are evenly populated as far as the orbitals are concerned, But once we get to the point where the orbitals are not equally populated, we start to see differences in their energies. If we zoom in on that one little piece, we can kind of correlate the population of those orbitals to what we may actually understand of their frontier molecular orbitals by either actually doing the calculation ab initio or symmetry group theory rules. The cool thing is that what you see here is that it is observed and predicted that the octahedral electronic configuration actually undergoes symmetry lowering such that the total energy of the molecule is lowered. And as a result, the geometry is changed. So I showed you an octahedral complex earlier. That is not its real geometry because the lowest energy electronic state is in a lower geometric model or orientation. And so what you can also see is that, hey, I don't have triply degenerate orbitals here. I have basically a single orbital, two presumably doubly degenerate orbitals, and then the two non-degenerate orbitals as well. And then you can actually convince yourself whether or not these are d-based orbitals by actually plotting their partial charge densities. And as you can see, if you squint, that these are all the molecular orbitals. And then one take-home thing to remind you is that these are all one electron molecular orbitals, right? Because you have your spin up and your spin down contributions. And so the reality here is that you have to use spin polarized computations if you're going to look at open shell systems. Otherwise, you will not get anything that's remotely close to real. Also, you can look at the partial charge densities to kind of get an idea of what do my molecular orbitals look like and what are the possible transitions that can arise from them. Questions?
But thanks, Zachary. You're a nice presentation. And questions are very welcome. Which means everyone is happy running spin polarized jobs and there are no questions. You were showing the orbitals.
Yes.
And those are for spin up.
Yes.
What is your instinct if one plots orbitals for spin down? Will they be exactly the same or slightly changed or drastically changed? Like, what are expectations? Can the orbital of the same symmetry, like with the symbols, repeat the same pattern of for up and down?
So, intuitively, you would think that yes, they should be mirror images of each other. One thing you can realize is that if you look at the dxy here, or the B2G orbital for the spin up, is of lower energy than what one would assume is the B2G orbital in the spin down. And that's likely due to it being occupied. So if we actually had these, if I actually had two electrons, it may be more mirror imaged. So the reality is, yes, they'll be very similar, but their energy ordering may not be the same due to occupancy.
Okay, more questions? I have one more.
Fantastic.
So here you are showing lines,
Yes.
discrete energies, and
Yes.
here you are showing profiles.
Yes.
What is the connection?
So the connection here is this is basically rigid. It is at the equilibrium point or the equilibrium geometry of the molecule. Here there is some thermal degrees of freedom that is taken into consideration.
Very good. Yep. But thanks, Zach.
What
Wait.
about
Go ahead.
Go ahead. Go
what
ahead.
about uncertainty?
Yes, because we are at very low temperatures in these calculations, if I recall, because we're not looking at room temperature calculations. At least this did not take into consideration room temperature calculations. So the uncertainty is intrinsic to this.
Okay, now let's finally thank Zach. And the next presenter, please come up and set up your presentation, is Seth Adrian, and he's opening another door for us. By now, we were focusing primarily on ground state or artificially populated excited states, but we were not looking on the response of the material to the external perturbation, such as photoexcitation. So this will open a door to explaining how material responds to light to matter interaction. What is it?
As you said, my name is Seth Adrian. So we're going to be looking at the light to matter interaction. So for this to actually occur, there has to be a transition dipole moment where it has to occur when the light hits. And the way we mathematically show this is you have your ground state and your excited states, and the dipole operator is in between them, and this all comes from symmetry basis. And as long as you get a non-zero product, that you have a transition dipole. And in very basic terms, like something you would teach to freshmen in chemistry, is your L quantum number has to go plus or minus 1, basically. And here I just show light coming in. You have an absorption that is roughly equal to the energy of the light. All right, so to develop your input files for generating these spectra, you make the states file, like half a dozen people have already talked about, and you VI it. And out of this, you need the number of states for later. You copy the states into an energy pop file. That's just how the script works, is it needs an energy pop file. Then you have to make this new file called VI input underscore overlap. You go 1, and then next line you have number of states, and then the last line you put another 1. And then you run the script OS underscore dipole underscore V3, which makes the OS strength file. And out of that, you need the number of transitions. So inside this OS strength file, there's some pretty interesting things. The first one is the first column here is I. That is the first molecular orbital where the electrons originally reside on. And then you go to your J, which is your second electron orbital, or your empty orbital, where the electrons go to. So in this case, it goes from 6 to 7. And then your third column here is oscillator strength. The oscillator strength is the probability of the calculated optical transition. And the oscillator strength is related to the transition dipole moment by a constant times the square of that transition dipole moment. And here you have your energy difference. This is the occupancy, so F sub I is there's 2 electrons in that orbital. F sub J, there's no electrons in that orbital, so it's going from I to J again. And then here's your coordinates to describe the orbitals. And then you generate a plot, which is using the script bin spectrum, and you have to answer the questions. Number of transitions, 36 in the case for me. And then you say how big a plot do you want. You can go 0.1 to 10, to get a fairly large range. And then you enter your width of each line, and you tell it, hey, my HOMO is in number 6. It runs a script. It generates this file, or it generates a file that you can pull out and work on in Excel or whatever your favorite system is. But we can use GNU plot to plot it, and that makes an SPE.ps file. You can include after the SPE an underscore nanometer if you are a traditional one or traditional absorbance spectroscopist, and you want to be able to see it in nanometers, and it's easier for you to think about, and then you convert to PDF and you get that bad boy over there.
Okay, but thanks. Is everyone happy? No, Levi is not happy, Aaron is not happy. Please go for
On
it.
slide 3, your third bullet. Slide 3. Oh, sorry, slide 4. This one doesn't have. Your third bullet, you say one number of states 1. What if you have, let's say, 2,000 states in your system that vary over at least 10, if not like 100 EV, and you only want to plot the states near the band gap, what do you need to do?
I'm sure probably just modify your states file. I think this number has to, because when you run this script, it pulls the things out of the states file, or the energy pot file actually. So if you don't have the same number, and it uses this file, so if you don't have the same number here as you have there, it's going to be angry with you.
Okay, so your answer to Levi's question is that if you want to narrow your window of orbitals, you trim your states file.
Yeah.
But then you're saying that this input overlap should match this
Yeah.
energy pop. So which numbers should be plugged into here and there if this states is trimmed? If it starts not from 1 but from 100.
So then go 100.
Yes, yes, very good. More questions?
Yeah, just so when it goes through transition, does it move both the electrons or just the one?
I'm not sure how it calculates it. I think it's both, but I'm not sure how it's actually calculating it in this. I think it basically is like Whitney's excited state where it moves.
Can you go backward one slide? And point on your blind cat, and then point finger on arrow. So it's just probability of transition.
Okay, so it's probability.
Oh,
okay, yeah.
I do have one question more.
Sure.
Can you go to the table of the transition dipoles? Yes, here. And you have named these 3 last columns coordinates. Are you sure, or you want to correct yourself?
That's not the right word. I don't remember the right
How
word.
are these 3 numbers connected with transition dipole?
Is it the orientation along which the transition dipole is changing?
Yes. Is transition num for given pair of orbitals? Would you agree that transition, I'm given 2 options, transition dipole is a number or it is a vector of 3 components?
It's a vector.
Where are these components in this file? Yes, let's thank that for the presentation. And the next presentation is by Levi Lustrom. So his talk is special in the following circumstances. In some sense, he summarizes 3 previous talks. What he is going to present will be connected to a talk by Whitney, because he is going to scroll through different electronic configurations. His talk is connected to Zach, because he is going to look on the spin resolved calculations. And his talk is connected to the presentation by Theth, because he is going to look on the response of the system to the light. So different configurations, spin and light. Floor is yours.
Thank you. So I'm going to look at this model just like Zach. It's titanium with 6 oxygens, 6 water. So since we need spin polarized calculations, first we need to figure out our multiplicity. And just like in the previous ones, you look at the number of unpaired, and you pretty much take the number of unpaired electrons, add 1, that's your multiplicity. So for all paired, it's singlet. If you have 1 unpaired, it's doublet. If you have 2 unpaired, it's triplet, and so forth. And this is just like if you have low spin or high spin, because this is a octahedral and this is a splitting. So we can either have, if we have all 4 d electrons, it can be a triplet, or if we excite it, then it can be a septet, or whatever 5 is. So to get spin polarized, you need to do this I spin equals 2. If you do not include this, it will say have everything paired. If you want to force your system to be in like a triplet state, you can say up down equals A, where for singlet A is 0 because it's taking the difference between the number of alpha and beta So to get from singlet to triplet, you say 2 because then you have 2 more in not paired. So from this, we can take our single point calculation, get our INCAR, and I wrote a script because I don't like answering questions. So I did this dot spin .sh, and I'll summarize what it does. It gets the bands, then it calculates the window that we're going to plot it at. It plots the DOS, which is here, and then it also calculates the spin polarized absorption spectra, and then it plots it. So the top here is the alpha beta components. The bottom is the average between it. And if you want to look into this script more, just open it up. But with the time restraints, I'm not going to go into a ton of detail on the script. So if we go to the singlet, as I said kind of before, when we have all 4 electrons, it wants to be in a triplet state. So between when we have the neutral complex, the singlet, if you don't specify, it will take the lowest energy configuration, and due to Hund's rule, it's not going to be 2 paired and then have an empty one. So for this one, it's pretty much the same spectra, but when we go to the first ionizer, we take a electron away, then they start to deviate, and right now it's a doublet, and we can see that from the DOS, there is a occupied state very close to the unoccupied for the spin up, but the spin down, there's a huge gap, and this will be constant, and we can see if we were to chop it off at like 4 electron volts, we would not see any contribution due to the spin down electrons. And so it's pretty much just the spin up that is contributing to the absorption. So then if we go to the quartet, or if we have 3 electrons not paired, the trend is pretty much the same, where the gap for spin down is too big to see it within a reasonable window. But if we go to the second ionized, where we'll go back to singlet or triplet, because in this case, again, for singlet for this molecule isn't the best, but we can see, since we're computational, we can force it to do whatever we want. We see that there is a very bright transition right away, and then this entire spectra has components due to spin up and spin down, because our unoccupied or HOMO is right next to the LUMOS, which is interesting. And then if we go to triplet, we see, just like in the doublet case, that the spin down is way into the absorption, and we only see spin up. And then if we go to the third case, we see similar case, just like the first ionized, where we have doublet and quartet, where most of it only comes from the spin-up electrons. So in conclusion, multiplicity is pretty much the number of unpaired plus 1. When you have higher multiplicity, you tend to have one spin component dominating the spectra at low energy. This DOS underscore spin.sh, I think it's very helpful because you don't have to do anything. You just have to hit it, and it does everything for you. So.
Thank you, right? For his community contribution to script development.
Oh, and this is in the bin.
And his presentation is open for discussion or hard questions if someone wants to give him a hard time.
Okay.
Or if something was not clear in the presentation, it is a chance to catch the speaker.
Yes.
You called high spin on slide 3. You called high spin excited state. Is that true?
No, it's just different configuration. It's how much magnetic field you have, kind of. Or you can get it with magnetic field.
There was a question from
Yes.
Zach.
So which spin configuration tends to be favored in the ground state?
Typically, I would believe low spin.
that always true?
I have no idea.
Let me reformulate question by that.
Yes.
How does the ground state configuration, low or high, relates to crystal field splitting?
If crystal field splitting is low, then it will be in high spin. If it's high, then it's be in low spin.
Good. More questions to Levi? I have a couple.
Okay.
So can you go to your spectrum?
Which one?
Any. So when we were hearing presentation by Seth, he was showing that he's finding the expectation value of transition dipole moment, and he's setting up a table with oscillator strengths, discrete correspondence between energy and oscillator strengths, and then he was converting it into continuous spectrum.
Yes.
Here you are showing 3 lines,
Yes.
and you're not showing where are they coming from. Can you explain what are you doing?
So we pretty much do the same thing as if we have non-polarized calculation, but in this case we can go from any state that is singly occupied to another state that is also singly occupied, but with the opposite spin. So when we calculate the oscillator strengths, the file has a lot more combinations that can occur. So these ones are only from singly occupied to not occupied states.
Do you observe spin forbidden transitions?
That would, you would have to open up the code that does this, and I didn't open the code because I didn't do it. And I think if you wanted to look at spin forbidden, you would need some perturbation to the crystal field, and I didn't do any perturbation, so.
Let's dig deeper, because I feel a little gap in our knowledge as a group. So you label here spec up and spec down. What does it mean? Where they are coming from?
So you promote a single electron from an orbital that's spin up to an empty orbital. So
Spin with spin?
spin up.
Okay, so spin is conserved.
Yes.
So Levi assumes that spin is a good quantum number and he is not flipping spin.
Yes.
Continue.
So spin down is the same, but it's down. And if you wanted to do a absorption that was a spin flip, so if you have a beta and you want to go to alpha, those are also calculated, but I didn't plot it.
We do not have it. Okay.
Yes.
So, do you have analog of oscillator strengths file, same as Seth did?
Yes.
How many?
2.
How do you get them?
You
Please teach us as a class.
you could go to the bin, and then there's a directory called spin, and there are 2 Fortran codes that you can run. One is spin up, one is spin down. You run it, you get the 2 oscillator strength files.
Good. Do they use the same input files or slightly different input files?
They use the same, with states being up and states being down.
So you have 2 replicas
Yes.
of orbital
Yes.
energies. One for up, another for down.
Yes.
And you tell that you were planning to show it, but there was limited time.
Yes.
Good.
If you're worried about it, open up the DOS spin, and it will explain it, hopefully. Or come talk to me.
So do you know the selection rules for spin forbidden and spin allowed transitions? Any criteria for spin allowed and spin forbidden?
I don't recall from physics, chemical physics. Yes. 1.
Plus or minus 1.
Yeah.
Is there a name associated with this selection rule?
Is it like spin allowed, spin up goes up to spin up, or the like some kind of?
If you have spin orbit coupling, you can do a lot more things, but in these codes, I do not believe there's spin orbit coupling.
Was the question? No. Okay, let's let Levi to relax a little. Let's thank him for setting up the questions. And we are very behind the schedule, and we have 3 talks more. Now we are opening another door. We are going to another challenge for characterizing materials. We are going to the barriers of reactions. We are going to breaking and forming chemical bonds. And we are using ab initio molecular dynamics as a tool to go through this type of challenges. First presentation is by Samuel Brown, and he will be the first to open the door in the world of molecular dynamics.
Hi, thanks. Yep, my name's Sam Brown. So I'm going to be doing some modeling molecular dynamics at or above room temperature. So basic of my talk basis will be setting the thermostat, how to increase the temperature on your models. So for any model or anything we do in VASP, as this has been mentioned several times before, you need 4 different files. You need the POSCAR, POTCAR, KPOINTS, and INCAR. And then to model molecular dynamics, there's like 3 different things that we'll need to do. We'll have to have a geometry optimized model, then we'll have to set the thermostat of that model, and then we'll have to do some molecular dynamics. And for each one of these 3 things, we'll have to have these 4 input files. So we're starting from, we're assuming we have a geometry optimized model, and now we're going to create the heating model. So in order to do that, we need to create those 4 models from before. So we need to copy in our INCAR and make that a POSCAR, and then copy over a POTCAR, which is the potentials, get the K points, and then we will need to open up the INCAR, which, as we all know, this is what actually does the different operations. So we're going to look into a little bit more of the INCAR. So this is the INCAR, and this is where we can kind of set the temperature that we want. So you probably can't see this, but right here it says TE-BEG, and that's the temperature beginning, and then right below that it says TE ending, and that'll be the ending temperature of your dynamics. So for this one I have it set, or it's initially start at 300 degrees, which is about room temperature, but we can change that to 3000 or whatever we want. Then over here we have NSW, which that's the number of steps. We can also change that. So for like this example, I set it from 300 to 50 just for computational reasons, and then below that we have the time step between each one of those. So when we run that, we get different files. We got this from the lab, the OSCAR file. So this shows the different iterations and the ways the ions move throughout the optimization. And for each one of these, we have a different temperature, and then so we can plot using NuPlot the temperature for these different time steps or iterations. So looking at this, you can see for the first one I did one at 300 degrees, then one at 1000 degrees, and then one at 3000. So it's kind of hard to see, but we have some pretty strong variations right off the bat, which then starts to level off around 300. Same thing, there's a lot of variations right off the bat, and then it levels off to about the temperature we want, and then again at 3000. So then after that, once we have, we ran that model, then we're going to put that into a molecular dynamics program. So again, we have the same thing where we're going to, we'll make a new directory, which has been shown before, so for molecular dynamics. Then we're going to copy over our 4 files, that what we just did in the last model. So we're going to copy over the INCAR into a POSCAR, copy the K points POTCAR, and then we're going to copy a new INCAR from the INCAR bin. And we'll look at that briefly. So for this, we have, this is the INCAR. There's another TE-BEG, which is initially set at 300. And we're going to change that to whatever temperature you want. So if you had your model initially at the thermostat, you want to change that to 3000 again. This this is for the temperature of the electrons, not the actual model. So that's something to note. And then again down here, you have the number of steps you can do. So after we adjust the INCAR, then you have your 4 files again. You can run that and get your output. And then you can view this watching a movie, which I think J-Bud's going to go over a little bit more detail. I tried a couple different ways to do this. Some didn't work. I worked with Molden. You can use the the command xdat to xyz to create a movie, and then you can view this in Molden, or you can look at like JMol, VWD. We'll look at this. So in one of my models, I looked at it in VWD, and then you can export that as a movie, which is what I have here. I think I can get it to play, and then you can just get it to dance around. How exciting!
Yeah, very exciting. Is there other conclusions?
That was it.
Okay. So, presentation by Sam is open for discussion and questions. I do have one, but I will ask after.
I was just gonna say, is there ever a reason to not have T beginning and T ending be the same, or temp begin, temp end?
If you were maybe wanting to ramp up slowly, do like an annealing type of process. So this one we just threw it down on the hot plate or whatever and then spiked it really high. But like some experiments that you might want to slowly ramp up and keep at temperature, then come back down.
Good. And at the board, you've told that random variations of temperature. Is there a single word to bring together all of those? If something suddenly spikes one side, another side, it's not a scientific question, it's more a linguistic question. How do you call it? Something?
Fluctuating.
Yes.
Say that again.
Fluctuation of
Oh.
energy.
Okay, thank you for presenting this stuff. Let's thank Sam once again. And next presentation is continuation of our moving forward toward the world of chemical reactions, bond breaking, bond formation, by Mohammed Abu Jabed, who will show us more details and more background of the molecular dynamics. Floor is yours.
Thank you, Dimitri. Thanks, Sam. Actually, is almost a repetition of previous talk. So this is actually math-intensive topics, but I'm not going to talk about any math. I'm just going to repeat all step how we'll calculate the heating and molecular dynamics and also continuation job. So as I said, for a VASP job, we need to file, postcard, KPOINT, and POTCAR. And so after each cycle, VASP write their geometry in the CONCAR file as a postcard format. So for any purpose, if we want to continue the job, we need to write a postcard file from the CONCAR of the previous job. So, and other thing is the same as the POTCAR and KPOINT is the same thing. But if we want to continuation an optimization job or the same thing, so we can use the WebCar file in the new directory. That will save our some time. Or if we don't the WebCar file, VASP will create the WebCar file again. And then just run the job. That's all for a continuation job. For heating system, and in all calculation, Gaussian job calculation or geometry optimization, we do that calculation in 0 degree Kelvin. But for real system, if you want to compare practical, we need to move our system to higher temperature to put the high temperature, some kinetic energy. So that's why we need the heating of the system, and Sam already described this all step. We need to copy the CONCAR file to the new directory as a postcard, and we need to use the KPOINT and POTCAR, but we shouldn't be use a WebCar file from the previous job, because change of the kinetic energy, the wave function also changed, so they will create the new. And we need to copy the INCAR file from this bin directory, is the Dimitri directory from the bin INCAR and INCAR heat, that INCAR file used as a input file for the VASP jobs, and then we need to run the job. And in the next one, I just put an example of the INCAR file. We need to, this is the POTIM, this is the time step in the femtosecond units, and this is the number of steps. If we want 100 steps, so it's going to be 15 and femtosecond. And we need to put the temperature, beginning and T back and T end, TE end. I put as a 2000 degree Celsius, sorry, in Kelvin, not Celsius. And this is showing a graphical presentation of the fluctuation of the temperature, as I said. In the first step, they put the 2000 temperature, 2000 degree Kelvin, 2000 Kelvin, But when you put the kinetic energy, this energy can be going to accumulate some potential energy, and then kinetic energies go down. That's why temperature is going down, and then the system will be heat again. So temperature will fluctuating. If we run the enough step, we will get a minimum fluctuation of energy, and we will get a stable heat energy. And then if we hit this system, then we use that geometry for molecular dynamics. To get the molecular dynamics, the same thing, just need to concat file as a postcode, and we need to use the different INCAR file. This name is the INCAR MD in the bin directory. And after this one, this all step will be saved as a x.car file. Then we will extract this all step in xyz coordinates, as in by running this script x.to_xyz is a Perl script to get a file name movie.xyz. Movie.xyz will contain all steps in a xyz format with energy and the time step as a frame. Then if we open this file in the VM, I use the VMD. We can use other software too, like VS or. Then in VMD, we can create an animation by this one. This VM, we can manipulate these graphics and everything else. But main position is we need to get an animation. Then it will make each frame, and then if we have an add-on, by adding this all frame, that will give us a movie like this one. This is not very exotic because this 2000 temperature is not enough to do any breakdown or anything else. That's why I'm showing this just vibration. Thank you. That's all.
We have one more slide.
Oh, okay. I thought that we are running out of time. So this is just showing the mathematical equation. How do you calculate this dynamics? First, by using the Newton's law of motions, we can know that by this one, change of the position with the time. This is called acceleration related with the force, and this force can be related to the gradient of the potential energy, and then finally this potential energy can be accelerated on the position of these ions.
Okay, well, thank Javed for the presentation. Any questions? Will the dynamics change if you change electronic configuration?
Sorry?
Will the trajectory change if you make it anion, cation, or excited state?
Yeah.
Yes. Let's thank Javed once again. So we have the last presentation by Brendan Disrupt, who will give us most important part of molecular dynamics, how to visualize, present, and upload it to YouTube channel if time allows. So it is most important practical steps that we need in completing of our research projects. Floor is yours.
All right. Videos. We've started on it a little bit with the last couple people, but we'll get a little bit more deep into it now. The couple ways I'm going to go over here are Molden, which has the benefit of being on the cluster, so you don't have to install anything yourself, and VMD, which you have to install yourself, and in some cases, like if you are using Windows machines, you might need to install VideoMock to actually produce your videos as well. All right, so the first thing you have to do is you have to take your molecular dynamics outputs and convert them over into the movie.xyz file, which is easy, just with the x.to_xyz command call. And then we get to go and start generating. This first one here is our look at Molden. When you open it up, you get something that looks like this. And there's three big points of interest that we can get from the Molden interface. This first one down here, the draw mode, lets you select what your model is going to look like. It starts out in the stick sort of configuration, but you can choose whatever you prefer. Then there's this movie button there, which will, and that whole section lets you navigate through the actual dynamics and all the different frames of calculation for your model. And then the red highlighted button is a toggle whether you actually like record each frame itself. So if you hit the red button and then the green button, you will record and print into your directory every frame of the calculation. After that, you need to condense all those frames into one continuous file, which that's really small, but the long line of code you can find in the advice for making a movie in the advice bin. Just copy it down and put your file name at the end. Yeah. Now to VMD, which has more options to it. First, you have to start out with uploading your molecule into VMD itself. So you go new molecule, browse to find wherever your movie.xyz is, saved, load it up, and then you get to choose your representation, and there's a dozen or more different drawing configurations. I like the CPK because it's normal ball and stick model. Then we get to start to actually make the movie here. Under extensions and visualization, there's the movie maker. You just click it, it'll bring up this screen here. You have to set two things right away. The working directory, which is where your files are going to be saved, and the name of the file which you're going to be saving. Then, if you go to the movie settings and go down, you can select different types of the movie that you'd produce, and then you make the movie. And we'll get to the different types in a second here, but when you make the movie, your computer might not recognize the video mock which you have installed. If that happens, you just say, oh, it's okay, I know where it is, because you're good at computers, and you can go into the directory in your programs file and specify for it. And then it'll bring up video mock, and you can just hit start and it'll record it, or you can change the video format. And then there you go, you got lots of different ones. Here's the Molden one. It's just a simple trajectory, starts at the beginning and slowly goes to the end. That's the same as this one made in VMD, but the VMD one's a little quicker, a little smoother. The trajectory rock, which is one of the options in VMD, will play just like the trajectory, but once it reaches the end, it plays in reverse to get back to your starting point. And then, like this rock and roll format here, isn't actually dynamics at all. It just like kind of moves the camera around the first frame. And that's it.
Okay, let's thank Brent. And are there any questions to the practical aspects of creating movies? Last chance? No? What is the difference between force field molecular dynamics and ab initio molecular dynamics?
Force field doesn't allow bonds to be formed or broken.
Yes, correct. Let's thank Brendan once again for presentation. And with this, thank you. I would like to conclude that through series of the nicely prepared presentations and discussion session, we were able to expand our abilities to model materials from just chemical models to the spin polarized models, magnetic materials, to the models that break bonds, and to the models that are periodic in space. So with this software, we can model anything: solid, liquid, gas, their interfaces. And I would like to announce a great success and hope that you've learned a lot from each other. And with this, we will be able to go to the small research projects as a part of the course. Lecture number 23 is finished. And let me announce the end of the meeting. Adjourn. I'm thanking all of the speakers.